Okay, so all the idea now is to evaluate if a certain transformation, you can see it right over here, satisfy three things. One, self-adjoint. Second, unitary. And third, normal. We are working on the space of the matrices over the real numbers. We define the inner product of a matrices by the trace of the transpose of B times A. And we are looking on the transformation SA, which equals A minus A transpose divided by 2 for any A in our space. Now, is this S transformation is self-adjoint? Is it unitary? Is it normal? We start with self-adjoint. Remember, by definition, self-adjoint that means that the transformations equal its adjoint. It's complex conjugate transpose, or in the real numbers, just transpose. You can also prove it by showing this. Because remember that if we're talking about a transformation, its adjoint satisfies that it equals A adjoint of T of B. And for a self-adjoint transformation, this T equals this T star. So let's try to find it. Let's try to calculate it. If the inner product of SAB equals inner product of ASB. So when we calculate SAB, we are getting this. Using linearity, we are getting to this one. Calculating ASB, given with this. Using linearity, we are getting to this one. Now the question is this thing equals this? The only problem is this little right side here. They are not equal. Or they at least doesn't seem right away equal. The left side is okay, it equals. So let's see if the right side equals. Let's calculate. Is this one equals this? Starting with this, right from here, we are getting, by definition of inner product of matrices, that it equals this trace. The right side, when we calculate, equals the trace of BA. Remember the rules for trace. The rules for trace states their trace of xy equals trace of yx is cyclic, and the trace of x transpose equals the trace of x for matrices. So when we look on this, we're getting that it equals the trace of BA. And why? Because if you look on this, it's just the transpose of AB. But as we said, the trace of a transpose equals the trace itself. And as we also said, we can move the matrices in the trace cyclically. So trace of AB equals trace of BA. And here we got, namely, this holds. The transformation is self-adjoint. What about unitary? Unitary means that T star T equals I, namely T star, the adjoint, is the inverse of the transformation. We saw that S is self-adjoint. The S star equals S. So if we plug it in and say that S star equals S, the condition for unitary becomes S squared equal I. So let's calculate S squared. Let's define B to be SA, which is the SA we have. A minus A transpose divided by 2. When we take the B transpose, you can see what we get. We get minus B. Namely, this is a skew symmetric matrix. This A minus A transpose divided by 2. So B, which is defined by this, is skew symmetric. Its transpose equals minus itself. Now, when we take it to squared, we are squaring B, or we are taking the transformation S of B. This is the square of the transformation. Remember how we define B. Therefore, S of B equals B minus B transpose divided by 2. But we remember, B transpose equals minus itself. It's Q-symmetric matrix. So instead of writing here minus B transpose, it becomes plus B. So it's 2B divided by 2. So we got B. We got SA because B was defined as SA. It means that S squared equals S. So we got S squared equals S. By the way, this is the definition for a projection operator. But remember, for a unitary, we wanted this one. And because S is self-adjoint, we just say we need S squared equals I. But we got S squared equals S, not I. So now the question is, wait a minute. Maybe S is the identity? The answer is no. Take the identity, apply S to it. You should get the identity, but you get 0. So S is not the identity. Here, we have something other than the identity matrix. So S is not unitary. S squared doesn't equal I. Or more specifically, S adjoint S doesn't equal I. Conclusion, no, S is not unitary. What about normality? Does it hold? S is normal? Remember the definition for normal? The transformation adjoint times the transformation should equal the transformation times the transformation adjoint. In our case, remember, the transformation is self-adjoint. So it becomes that S star S equals S times S equals S squared. And for the other side, we apply S to it. Again, S is self-adjoint. S star equals S. So SS star equals SS equals S squared. On both sides, we got S squared. Namely, both sides are equal. This is exactly the definition for a normal matrix. Remember that self-adjoint is by definition a type of a normal matrix. a type of a normal transformation. So we should have expected this. Any self-adjoint operator is necessarily normal. So yes, S is normal. So summing it all up, else satisfies this, the definition for self-adjoint. S squared equals S is the projection operator, but it does not equals I, so it's not unitary, or above the real numbers, it's not orthogonal. But indeed, S is normal. It satisfies the definition for normality. Especially we knew that because S is self-adjoint. Self-adjoint is a type of normal transformation. And that sums it all up. Thank you all very much. If there are any mistakes or correction, please tell me. And for Gemini, for writing it down. Thank you for watching. Thank you all. That's it.